Hello everyone and welcome to this lesson. In today's lesson, we will be learning applications of derivatives in cone and half cylinder. So we'll start with the problem. A cone of maximum volume is inscribed in a sphere. Prove that the ratio of the height of the cone to the diameter of the sphere is 2/3. So we have a cone inscribed in a sphere, and small x, this is small x, r is the radius of the cone, and capital R is the radius of the sphere. So using Pythagoras theorem, x squared plus r squared equal to capital R squared. Now we have the cone has the maximum volume. Volume of a cone is 1/3 pi r squared into height. So now h I can write as capital R plus x because this is h, the height of the cone. And small r squared I can write as capital R squared minus x squared. So this becomes 1/3 pi capital R squared minus x squared into capital R plus x. So opening the bracket, you get 1/3 pi r cubed plus r squared x minus r x squared minus x cubed. So we have converted the volume to one variable, that is x. Now calculate dv by dx, that is 1/3 pi. It will give you this a constant r cubed. So you get r squared minus 2rx minus 3x squared. Call this as equation 1, we'll come back to it later. Equating dv by dr to 0, you get r squared minus 2rx minus 3x squared is 0. So factorizing, you get r minus 3x into r plus x is 0. So r is 3x or r is minus x. R cannot be negative, so we take r as 3x. And now we will calculate d2v by dx squared, and for that I will use equation 1. So that will be 1/3 pi minus 2r minus 6x, which in any case is negative. So the volume is maximum. And what do we have to find? Going back to the question, we have to find the ratio of the height of the cone to the diameter of the sphere. So height of the cone is capital R plus x, that is capital R plus x is r/3, which is 4r/3. So the ratio of the height of the cone to the diameter of the sphere will be h/2r, that is 4r/3/2r, which is 2/3. So the ratio is 2:3. Coming to the next question, this is on a half cylinder. A given quantity of metal is to be cast into a solid half-circular cylinder with a rectangular base and semicircular ends. If the total surface area is minimum, prove that the ratio of the length of the cylinder to the diameter of the semicircular ends is pi is to pi plus 2. Now we need to remember this formula. Total surface area of a half-circular cylinder will be pi r squared plus pi rh plus 2rh. So it's basically half the total surface area, but you have a 2rh, where 2rh stands for the bottom rectangle. So we have the volume is given to be 1/2 pi r squared h for a half cylinder. So h will be 2v by pi r squared. And so we have this formula, we have to minimize the surface area. So in the surface area formula, instead of h, I will put 2v by pi r squared. Why are we doing this? Just to reduce everything to one variable. So s equal to pi r squared plus pi r 2v by pi r squared plus 2r 2v by pi r squared. So this is pi r squared plus 2v by r plus 4v by pi r. And now calculate ds by dr, that will be 2 pi r minus 2v by r squared. ddr of 1 by r is minus 1 by r squared minus 4v by pi r squared. Equate ds by dr to 0, so you can divide by 2, so you get pi r minus v by r squared minus 2v by pi r squared is 0. So pi r will be v by r squared plus 2v by pi r squared. Now cross multiplying, you get pi r cubed is v plus 2v by pi. So now substitute for v. V is 1/2 pi r squared h. Here also you substitute. So you will get that this 2 gets cancelled, pi gets cancelled, r squared also gets cancelled. You get pi r is pi/2 h plus h. So pi r will be h into, take the LCM, pi plus 2/2. So pi by 2r will be h by pi plus 2. Basically you have h by 2r is pi by pi plus 2. And now calculate d2s by dr squared. For that I will use this. So that will be 2 pi minus 2 into ddr of r raised to minus 2 is minus 2 r raised to minus 3. So using this, you get it as 2v minus 2v minus 2 r raised to minus 3. Again minus 4v by pi into minus 2 r raised to minus 3. So this is 2 pi plus 4v by r cubed plus 8v by pi r cubed, which is greater than 0. So surface area is minimum when the ratio of the length of the diameter, that is h, to the diameter of the semicircular ends, this is 2r, is pi is to pi plus 2. That is what we have to prove. So we have seen applications of derivatives in the problems involving cone and sphere and also a half circular cylinder. Thank you.